Hello, friends. Welcome to Science Talk. I am your host and resident oceanographer, Jim Massey. Okay, I want to discuss with you this summary report of an extremely lengthy paper, and this appeared in the online journal EOS. And what are we talking about here? Tracking heat gains and losses in the Nordic Seas. The Nordic Seas experience influxes of warm water, for example, like the Barents Sea, right? And losses of heat to the atmosphere with knock-on effects on sea ice, glacier retreat, and carbon dioxide uptake. And it was published at the end of January of this year. Lars Smedrud, who is also the lead author on the very lengthy paper that he is summarizing here. So here is a picture of Arctic sea ice. Wee bit of open water here, as you can see. Not sure what time of year this photo was made. Warm ocean currents flow poleward, cold water flows equatorward on planet Earth. Well, traditionally. In the North Atlantic, warm water flows from the Caribbean to the Nordic and Arctic seas. A recent article published in Review of Geophysics examines this flow of Atlantic water and its knock-on effects, such as heat loss to the atmosphere, decrease of Arctic sea ice, and the retreat of Greenland glaciers. We asked the lead author some questions about these processes and how they have changed over time. Now, we're going to go through this here, then I'm going to show you what the article is based on. And I was considering preparing videos discussing this article. Then I realized that I probably would have ended up talking for 6 to 7 hours. It is that extensive of a paper. It took me 3-4 days to really go through it in detail, to analyze the graphics and so on. It's an incredible piece of work. It's not only it's not just a literature review, which it is, and a very extensive one, but it's also featuring new research. So it's a combination of discussing their research with an extensive literature review. Quite the piece of work. Quite excellent. So why does warm ocean water flow towards the pole, and what happens when it gets there? Warm ocean water flows toward the poles because it is pushed. The pushing is done by wind forcing, differences in sea surface height. Okay, let's stop right there. The differences in sea surface height, that sets up what we call a pressure gradient. And a pressure gradient, water tends to flow down the pressure gradient. So where the sea surface height is taller, well, it exerts more pressure on whatever level, whatever depth in the water column you want to choose. If you're 20 meters down, okay, a taller water column will exert more pressure than a lower water column on that 20-meter line there. But the point is, it's greater in pressure, and it follows the pressure gradient. Then picture this on a massive region. You have Coriolis acting on it. Coriolis deflects movement to the right in the northern hemisphere. So when we're really talking about these movements of currents, etc., we're talking about balancing the wind stress, wind forcing. That's wind stress, wind blowing across the water. We're talking about balancing Coriolis. We're talking about also the pressure gradient as well as vorticity, which is a tendency to rotate. So all these things have to be balanced, and plus the fact the Earth's rotating, it's a spheroid, oblate spheroid object. So when you have liquid sloshing around, it's going to be moving. So in warmer regions, the water expands, sea level rises. Well, that makes perfect sense. Colder regions, water is compressed, sea level is lower. Higher, lower. There's your pressure gradient. Another type of pressure gradient. There is a gradual cooling of the water along the way. In the case of the Atlantic Ocean up to the Arctic, the warm water starts in the Gulf of Mexico at about 30 C, quite warm, eventually reaches the freezing point at about minus 1.8 C around Svalbard. The ocean carries a lot of heat this way. This cycle contributes to keeping mainland Europe and Scandinavia much warmer than they would have been without these currents because when this water returns south, it is much colder. So, what are the characteristics of this heat flow in the Arctic Ocean? Within the Arctic Ocean, the general flow is influenced by a large flux of fresh water added to the surface from river inflow, rain, melting glaciers, other forms of precipitation. This fresh water creates a fresh estuarine surface outflow influenced by the Coriolis. Um, I would not use the word force. It's not a force, it's an effect. It's more accurate to say the Coriolis effect, and therefore remains close to the Greenland and the Canadian side. While the warm inflow is always found on the east side of the Nordic Seas along the coast of Norway, note that the Nordic Seas are an important part of the Arctic Ocean and that the name Arctic Mediterranean has also been frequently used to describe this body of water. How has heat transport affected Arctic sea ice cover over the past century? His response: there is a close relationship between northward ocean heat transport and the heat gained by the atmosphere above the Arctic Ocean. When the sea ice cover decreases, there is a larger area of open water available for cooling, leading to increases in total cooling. We found a surprisingly large increase from about 150 terawatts around the year 1900 to about 200 terawatts in the recent decades, about a 33% increase. We can't really say that the sea ice loss has caused the increase in heat loss and heat transport, just that they're congruent. Now, this may sound a little counterintuitive. Increases in total cooling. What they're talking about is that the heat contained within the water itself diffuses, it fluxes to the atmosphere. Well, if you're moving heat from A to B, B warms up, A cools down. So, they're talking about the loss of heat. Yes, the water loses the heat to the atmosphere. In so doing, it cools. And if it's cooler, of course, it's going to be more dense. The question then becomes, does it sink? Well, the answer depends on the salinity, on how much ice melt you got going on. And we're finding effects that the halocline is changing around with all these mechanisms taking place. So, you've heard me discuss with you before, that they got the oceans are warmer. They're bringing in this warming water right into places like the Arctic Ocean, and that heat is diffusing. It's either melting the ice or if it's open water, preventing ice from forming. Well, you know what? That heat continues into the atmosphere, and you're going to continue warming the Arctic atmosphere, and that's going to lead to increased thawing of the permafrost and so on and so forth. And, we know that what happens in the Arctic does not stay in the Arctic. You get this Arctic amplification, and you start seeing what we are seeing around the planet. Crazy jet streams going all over the place. Places becoming really wild precipitation events, wetter, maybe drier, drought conditions. We're seeing all sorts of crazy things because the heat distribution on the planet, within the planet system, is rapidly changing. So I just wanted to clarify what he's driving at here, that the cooling is the oceanic water cooling because it gives off its heat to the atmosphere. So I'll show you, some of the things in that paper, but they talk about, heat flux loss that's going from the water to the atmosphere. So include this little diagram. So here's a topography. The darker blue is the deeper regions, and here's the Eurasian side, the North American side, Greenland, Okay, it is the land of ice, Iceland, right? Through Fram, etc. You see this light blue all over the place? Okay, that's your shelf system. So here's the East Siberian, the Laptev, the Kara, the, you know, the Barents, right? You got that all here, right? All these very shallow coastal areas. We got the permafrost, the warmer water is thawing out the permafrost there, releasing methane. So now, during glaciation periods, when there's ice sheets on the continent, sea levels are drastically lowered. This all gets exposed. This all comes. So you get this one big land region all through here, leaving pretty much just this little puddle, you know, for your Arctic Ocean, which really is more like an Arctic Sea at that point. And you can see this becomes shallow. This almost gets closed off. So that really the only communication is right here through Fram. All this almost gets closed off. So, okay, let's look at these. The red arrows are warm waters coming in. The blue arrows are cold waters leaving. So you have this major push, about 9.5 sphere drips coming in. This is the Barents Sea region. And so you got some flows through the shelf regions, about 3.2, 2.4 sphere drips. Some gets entrained within here. Right? You have some flow following the current that basically runs along the shelf break margin, because water comes in and it flows counterclockwise, kind of goes in this direction, even though we then have the Beaufort gyre, which goes clockwise here. But that's another set of mechanisms for that. Here's the indication of 0.7 sphere drift through Bering. We know that this is increasing due to the work of Rebecca Woodgate. And here's some of the outflow. So we have 1.7 sphere drift through the Canadian archipelago, 4.7 basically, comes in this way, see ya, going out that way, and, going to more southerly latitudes. On this side here, this is basically, the heat flux to the atmosphere. So you got 16 terawatts over this green region, 17 terawatts over this blue region, 115. This is basically the Barents Sea, 56 terawatts going into the Kara Sea, over the region like Novaya Zemlya and so on. Not surprisingly, the largest amount is of heat flux to the atmosphere, or as they say in the paper, heat loss to the atmosphere, is in the Barents Sea, because this is where you're going to see the greatest temperature differential, because the water is warmest here, gives off its heat. As it continues flowing this way, it cools down. There's less heat to diffuse flux to the atmosphere. The next question is, what drives the variability in ocean heat loss? The year-to-year variability is dominated by cold air outbreaks. They actually call this, they actually abbreviate CAOs. Seriously, they do. In the Nordic seas. The long-term increase in heat loss is related to the increased ocean heat transport. This is important. And Arctic sea ice loss. Okay? The long-term increase in heat loss is related to the increased ocean heat transport and the Arctic sea ice loss. And you've heard me discuss this with you countless times before, but this is an important principle, and it needs to be remembered. This sea ice loss has occurred mostly in the Barents Sea. The increased ocean heat transport is again at least partly driven by increased wind forcing around the Shetland Island west of Norway. How do CAOs, cold air outbreaks, impact climate? The cold air outbreaks occur when cold air masses blow southwards from the sea ice covered part of the polar ocean and out over warm ocean waters in the Barents and Nordic seas. They occur as the cold side of low pressure systems in the atmosphere and produce really intense events of ocean heat loss approaching 1,000 watts per square meter. 1,000 watts per square meter. That's a wee bit. Most of the short-term variability and heat loss from the Nordic seas are explained by these events. Short-term, okay? Now you have long-term, we got some decadal oscillations and fluctuations taking place. What are some of the unresolved questions where additional research data modeling is needed? And he then proceeds to state, what remains is to improve our confidence in future prediction. Our review found a somewhat surprising increase in ocean volume transport towards the Nordic seas. I've shown that with you in previous videos where I did deep dives into, the increased warmth and ocean volume going into the Arctic Ocean from both the Atlantic and the Pacific side. Okay, so we see this increase in ocean volume transport towards the Nordic Sea is an increase about 1 sphere drop. And as a reminder, a sphere drop is 1 million cubic meters per second flow. Now, it tells you the volume per second. It doesn't really tell you the velocity because it depends on if I have, a current that's say 1,000 meters, wide, and it's 1,000 meters deep. Okay, 1,000 times 1,000 cross sectional. That's a million cubic meters. So, well, the square area would be a million square meters, right? And then if I go 1 meter per second of that, then I get the 1 million cubic meters. So basically, my velocity in that situation would be 1 meter per second. But what if, and I'm doing this just to illustrate that sphere drift only tells you volume, not velocity. So what if it's 100 meters wide and 1,000 meters deep? Okay, so that's only 100,000 square meters. Well, then you need to have what? Be 10 meters of length to get to 1,000 cubic meters. So then your flow rate would be 10 meters per second. Same volume, but you have to look at the dimension as to if you want to get a handle on the velocity. But, the ocean's a pretty big place there. We just tend to stick to sphere drops to let us know that this many sphere drops, because it's telling us the volume. Oftentimes we're interested in the volume because with the volume, if you know the concentration, if you know the heat content, you then have an idea of total flux. And you can use those things to measure total flux. Remember, flux is a concentration that moves. So basically, if I have, let's say, a 1 molar concentration of whatever chemical, okay, so 1 molar concentration, per cubic meter, and that moves at, 3 meters a second. That's my flux rate. I have a concentration and I have a velocity or some sort of movement per unit time. That's a flux. So when I talk about heat flux, to the atmosphere, you're talking about watts per square meter per day, per second, per year. That's a flux. And that's what they do a lot of in that paper is they basically calculate watts per square meter per unit time. That's how you calculate a heat flux. So that's the general idea of flux. So the Gulf Stream starts at about 30 sphere drops east of New York, and the inflow to the Nordic seas is about 10 sphere drops. This increases at odds with the speculations that the 30, that should be 100. Because by the time the Gulf Stream starts out about like 15 in the Gulf of Mexico, and then due to Western intensification, gyres and Coriolis, etc., it speeds up to about 150 by Newfoundland, and then there's a bit of a slowdown as it swings over to like what would be like the eastern side of the gyre. So it's really, unless it's a drastic slowdown, I think the reporter might have be quoting this incorrectly. because from Newfoundland to the Nordic Seas is not that much of a distance. You know, he said it starts out and the inflow is about 100. Then he says this increase. Well, 30 to 10 is a decrease. So I'm thinking this should be 100. So I think it's an error on the reporter's part. So let's assume it goes from 30 to 100, which is, how I've always, understood the flow rates, because it does, as I said, the Gulf Stream speeds up to about 150 by Newfoundland as it starts to swing over to, Newfoundland to the Scandinavian side. You start getting to the eastern side of the gyro, so there is a slowdown. So I can see it going from 150 to 100, but 100 is still faster than 30, so you can increase from 30 to 100. That makes sense. So this increase is at odds with the speculations that the overturning in the North Atlantic may be slowing down. Well, isn't that interesting? Many people forget the horizontal part of the circulation with inflow in the east, outflow in the west. But apart from this, an increased future heat loss, i.e., from the water to the atmosphere, driven by the expected Arctic sea ice loss, may actually drive an overall stronger future inflow towards the Atlantic Ocean. In other words, an increased flow of water into the Arctic Ocean, and since the oceans are warming, that brings increased heat into the Arctic Ocean. That heat diffuses, it fluxes upwards, melts the ice, prevents the ice from forming, goes to the atmosphere, cooling down the water, which then leaves eventually at a lower temperature. And Lars S. Smisrud at the University of Bergen in Norway. So now, let me go to here. Paper in the AGU, Reviews of Geophysics. Nordic Sea's heat loss, Atlantic inflow, Arctic sea ice cover over the last century. There you see that gentleman again? See all authors. There's something like 46 authors on this thing. So here's the abstract. Poleward ocean heat transport is a key process in the Earth system. We detail and review northward Atlantic water flow, Arctic ocean heat transport, heat loss to the atmosphere since 1900 in relation to sea ice cover. Our synthesis is largely based on sea ice ocean model forced by a reanalysis atmosphere, so basically a 118-year record, corroborated by comprehensive hydrographic database 1950 onwards. Arctic water inflow observations starting in 96, and other long-term series of sea ice extent going back to 1900, glacier retreat back to 84, and Barents Sea hydrography going back to 1900. The Arctic Ocean, including the Nordic and Barents Seas, has warmed since the 1970s. This warming is congruent with increased ocean heat transport. Increased ocean heat transport and sea ice loss has contributed to the retreat of marine terminating glaciers on Greenland. Heat loss to the atmosphere is largest in the Nordic Seas, about 60%, with large variability linked to the frequency of CAO, cold air outbreaks, cyclones in the region, but there is no long-term statistically significant trend. Heat loss from the Barents Sea, about 30%, and Arctic seas further north, about 10%, is overall smaller, but exhibited large positive trends. In other words, there is a significant trend for that aspect. The Atlantic water inflow, total heat loss to the atmosphere, and dense outflow have all increased since 1900. These are consistently related through theoretical scaling, but the Atlantic water inflow increase is also wind-driven. The Arctic Ocean CO2 uptake has increased by about 30% over the last century, consistent with Arctic sea ice loss, allowing stronger air-sea interaction, and is about 8% of the global uptake. You don't have the ice there. You have the atmosphere and the oceans, interacting. There's winds, there's mixing, there's turbulence. That CO2 and other gases gets entrained into the water, into the ocean. And of course, CO2, we know what that does to oceanic pH. And they go through a plain language summary. It's saying the same thing. And then, excuse me, then they go through an introduction and focus, and they have this nice little model here, which is very similar to the one I showed you over here. Um, where is it? Yeah, this one here. This is like looking down on it, and this one is so it's more like a 3D graphic of it. But you can see, the 1.9 outflow here. Here's showing some heat fluxes that way. Is that zero point 0.7 from the Pacific side? This represents the pycnocline, the influx of the warm Atlantic water. It will eventually work its way around this way. And this is the Lomonosov Ridge, it's Fram Strait, etc. So they showed a schematic overview showing the losses. So, there is just chockloads of information in here. And we just saw that diagram. So they pinched that from here, did a little featured article I just shared with you. And review of relevant processes and conditions. And again, very extensive literature review. I like the fact that they cite papers from, a long time ago, like Mosby in 1962, which is basically 60 years now. They even go further back. So they didn't just look at, a lot of times you see papers, they look at stuff in the last 10 years when they do the literature, and they're forgetting oftentimes that just because something might be 20, 30 years old does not mean it's any less pertinent. All knowledge is, you build on knowledge, no matter how far back it took place. So Bjerknes, very prominent oceanographer in the day, he did a lot of, you could say, groundbreaking work on this issue here. So, this is, they're talking about meridional heat transport, atmospheric forcing, and they bring in, credit to them, they bring in a North Atlantic oscillation, they bring in the Arctic oscillation. So they talk about these, oscillatory systems, how they affect matters. CAOs, right, cold air outbreaks. So they talk about all these things. So they're actually synthesizing atmospheric processes affecting oceanic processes, and then how the oceanic processes affect the atmospheric processes, how they interact, and the effects of all of that. So, this is a Herculean effort here, and they're to be commended. Arctic sea ice loss is, apparent throughout the year, so they look at the cryospheric aspects, and they go on. Now, if you had an idea, okay, like these little bars tells you how much you scroll down. Okay, I hardly scroll down any. So they go on, and the ocean, Atlantic inflow to the Nordic seas, heat fluxes and cooling of the Atlantic inflow, etc. And then they analyze the heat fluxes, give some graphic, total annual heat loss. They break it down: Arctic Ocean overall, Polar Sea, the Barents in black, and the red is in Nordic seas. And, with some regression lines fitted through. And then we get into some math. And for those of you who want to do some integration, here you go. The double integral. So, basically, this first integral, one on the right here, from minus h to z refers to the dz prime, and minus h to 0 refers to dz. So basically, from whatever depth of interest to some significant depth, could be like a halocline depth, what have you, and then the total from the depth of interest all the way up to the surface. G, of course, is the gravitational constant. F is the Coriolis parameter. And then this is row references, the reference density. These are treated as constants. And the Coriolis parameter is defined as 2 omega sine phi, where sine phi is the latitude. So if you're at 80 degrees north latitude, then you take the sine of 80 degrees, right? Converting, of course, to radians first. And then the 2 omega. Omega is basically the angular momentum of the planet itself. And that's a constant as well. And then they talk about how the Atlantic water transforms into other waters as well. It said this is an incredibly in-depth paper. Here's a view. So now we're looking at net surface heat flux in watts per square meter. You can see, obviously, the furthest, you can see how the oceanic waters loses the heat as it moves northward, but you can still see, here's the Nordic Seas getting into the Barents over here. You can still see the major loss of heat taking place. And of course, sea ice is indicated. And they talk about CO2 uptake in relation to heat loss. That's the mixing, increasing the concentration. And we finally get into the methods. So they talk about what computer models they used. As I said, it took me, 3 days of reading this in detail and scrutinizing, studying the graphics, etc., to see what they were doing. And I gave serious thought to presenting this, but I probably would have had to break this video up into 4, 5, or 6 parts. And I've been like insane. So I was glad to see the little Q&A, which nicely summarizes, the the essential take-home messages. And then this figure shows some ocean heat transport overturning. That's the vertical mixing from the gyra that moves around in the Arctic Ocean. And then we have some CO2 flux, which is in megatons of carbon per year. For the CO2 uptake is a function of simulated Norwegian Earth system model. That's the NORESM short. Surface forcing for the Barents and polar seas, the most important parameter, sea ice cover. Whereas in the Nordic seas, heat loss is best at explaining observed variability. The negative values show ocean uptake of CO2. What we're seeing here. And then they're plotting the cold air outbreaks in terms of anomalies. So CO2 observations do estimate. It's only like halfway down. Now I'm just doing a skimming over and look how long it's taking. Right? Ocean ice sheet interaction. Then we finally get to results. And then they go through looking at it from the centennial, surface cooling, and they describe their findings this way. They still continue. Then they talk about ocean temperature, sea ice extent, ocean heat transport, with more. Uh, what they have here is potential temperature, practical salinity. This is a TS curve, okay? And these lines that you see here with value 26.4, 26.6, etc., these are what we call isopycnals. So these are density. So this would be 1,026.4 kilogram per cubic meter. So we just dropped a 1 0. That's a convention us oceanographers do. And they're basically showing you that, shows how temperature and salinity affect the density. The Atlantic water is warmer. The outflow water, that's where it cools down, is going to be cooler. Okay, and because it's cooler, you're going to probably see a little increase in density. But remember, seawater density is a function of the temperature and the salinity. For those of you who might not have seen my videos on, overturn mixing and stratification, as well as salinity explained, please go check those out. We talk about dense water formation, how the Atlantic water is transformed to denser but also fresh water because of maybe the sea ice melt puts the fresh water land. You got riverine input, you got precipitation, etc. And that's why we see the slightly reduced salinity values that give you slightly reduced density values up there. And talk about atmospheric circulation and so on. So it's a very extensive paper, lots of chock full loads of information. If you guys want, I can leave the URL link in the comments section, as I typically do. If you're really really bored and got a week of time to kill, I said I found this paper to be an excellent piece of work. Some very fascinating, interesting findings, and very important contribution to our understanding of what's happening in the Arctic. So they did the centennial analyses. Now they do the looking at the analyses of this century. And again, they did go through basically the same kind of breakdown, same kind of analyses of the different aspects they were interested in. And this is showing, figure 12, 12A, figure 12, inflow function of heat loss. So they're showing the heat loss in watts per square meter. And this is just showing some more data points. And then they talk about the halting Barents Sea cooling machine. Now they say the heat loss was reduced in the OOs compared to the 80s and 90s, the extent that total Barents Sea heat loss decreased in recent decades. In other words, the flux to the atmosphere was reduced. But that then warmed the denser water exiting the polar sea. Because if the heat didn't go to the atmosphere, it stayed in the ocean. So the major change was an increase in sensible heat flux. That's an interesting finding. And they go on to give their hypotheses as to why that result was noticed, was observed. So now we finally get to the discussion. Try to pull this all together. And they just continue to go on. Very, very detailed. And I said, if I had done this, to do this video, to analyze this paper and give it its due that it deserves and give it a full treatment, this would have been a very, very lengthy video, probably 5 to 6 hours. It's just so much information in this. So, yeah. Oh, yeah. Finally, we get to the conclusion. And and this repeats a lot what was covered in the abstract, what was covered in that little Q&A article we discussed at the beginning. Sea ice covered the Arctic is set to further decrease in the future. This will contribute to more open water and larger ocean heat loss, i.e., heat flux from the ocean to the atmosphere. And it's talking about baroclinic inflow. There's baroclinic, there's barotropic. That involves physics of the oceans and the isopycnals. The math can get to be challenging with that. And then they, supported by the Berkman Center for Climate Research, that gentleman whose papers, they were citing from the early 60s. They named the center in his honor. Rightly so. He was a pioneer, along there with Henry Stommel and Sverdrup himself. So you can see, the very, very lengthy paper. But they did this major synthesis of all the knowledge of the aspects they examined to this point, looked at how it related to their study, how their study compares to them, and helped contribute better to our understanding, our knowledge of what's happening in the Arctic region. So, basically, the waters are warming, that heat is diffusing to the atmosphere. That's kind of, when I simplify it like that, it sounds like a duh, but sometimes you have to go through, you can't just say something without backing it up. And this has loads and loads of data to back it up. Okay? And this is something I've been discussing with you guys for quite some time now, so that you probably know the mechanisms better than I do. Okay. Kind of joking around there. But that's the main thing. The heat's fluxing out. And I showed you in that little simplistic diagram at the end of my recent my updated ocean heat content, where that heat in the ocean does diffuse to the atmosphere, and it can take and it'll do so for centuries, if not millennia. So we've locked the planet into a warming trajectory of at least 5°C by 2100, to be quite blunt. All right. I think I've gone on long enough here. Thank you for your time. Hello folks, this is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.